Okay, thus far in the organometallics unit, we've talked about two types of reagents, Grignard reagents and organolithiums. And we have already discussed their reactions with these types of oxygen-containing compounds. We have not talked about a third type of organometallic that's not seen on this screen. That is called a GILMAN reagent. And the GILMAN reagent has a little bit of an odd form. Another name that you could have for the GILMAN reagent is an organocuprate. So it's going to have copper in it. And the form of a GILMAN, from now on I'll just call it the GILMAN. The form of a GILMAN is a little bit unusual, and it can be represented in a couple different ways. Let's say we have an ethyl GILMAN reagent. So the ethyl GILMAN reagent could look like this. Okay. Within the parentheses, we have the two carbons representing the ethyl group. You could have two of those, and it's connected to a complex copper lithium. That's one way. All right. You can probably tell now this is a little bit more complicated than a Grignard or an organolithium. And you would want to get this, you don't want to lose any points by misrepresenting a GILMAN reagent. Another way you could represent this is draw it out like this. And you could draw out literally both ethyl groups. The last way is this. I'm trying to see if I have this in my notes. You could have a copper in the middle. It's a little bit odd, but this would be negative, and then you'll have a lithium plus as a counter ion. My preference is this with the parentheses, and the idea here is that you still have a carbon that's partial negative, okay, partial negative charge, because that's connected to the metal, and that carbon and whatever it's attached to will be delivered to the, we'll call it the substrate or the electrophile. Okay, that's another weird thing about the GILMAN. We're not going to be attacking carbonyl groups. We're not attacking aldehydes or ketones or epoxides or carbon dioxide. So it's totally different than what we've seen with the Grignard and the organolithium. Let me show you how to make the GILMAN reagent, and I believe we are up to reaction. Give me 1 second. Reaction G. Yeah, so reaction F was the one with carbon dioxide. This is reaction G. And we are going to first synthesize GILMAN reagent. You're going to synthesize the GILMAN reagent from an alkyl halide. Take a look at our example here. So let's make that one. Let's take an alkyl halide that has two carbons, either chlorine or bromine, and we are going to convert it first to a organolithium. And this one you know already. Okay. Next, we are going to add copper iodide. And that's how you form the GILMAN reagent. Don't worry about stoichiometry. Obviously, you'll need two of the organolithiums for every copper iodide. But let me draw it the way I like to draw it with the parentheses. Just make sure that that second carbon is totally within the parentheses. Okay, you don't want to split the atom. You want to be very unambiguous. What are you adding to our substrate? And then here we have copper lithium. Now we can actually balance this because you make lithium iodide, and those ratios work out. That's it. No mechanism. Don't worry about the mechanism for the synthesis of the GILMAN, and actually don't worry about the mechanism when we use the GILMAN reagent. This is reaction H. How can I say this? Use GILMAN to make, we're going to make a hydrocarbon. We're not going to make an alcohol like we did with the Grignard and the organolithium. We're just going to make up a straight hydrocarbon, a plain hydrocarbon. Now, it doesn't have to be all single bonds. It doesn't have to be an alkane. It could be an alkene. It could be an alkyne. Let me show you an example of that. Let's take the GILMAN reagent that we made, and we are just going to react it with a alkyl halide, any alkyl halide. The GILMAN reagent we just made was this. Again, be very careful with your parentheses. And I'm trying to think if we need to do anything else. There is no alcohol, right? Because then we're not going to have a second step where we need to protonate it. There's no oxygen source. I think that's it. Or I'm going to say that's it. Alkyl halide. Let's list the types of molecules. Alkyl halide and GILMAN. This is still an umpalung. We still reverse the polarity, and this carbon is partial negative. Normally, in all the previous examples, in organic 1 and organic 2, this carbon was partial positive. It attracted a nucleophile. This is the carbon that's attracting the nucleophile. This carbon is partial positive. This carbon is partial negative, and all you have to do is just make sure you have the right number of carbons. That dot connects to this carbon within the parentheses, and that carbon is connected to a methyl group. If you count up your carbons, this is C5 plus C2 goes to C7. Okay. Yes, those of you who are very observant, it's kind of wasteful because your GILMAN reagent is dead after you transfer one of the alkyl groups. So you do lose the ability to add all the carbons. So only add one R group, one alkyl group. Still, this is a very convenient way to make a hydrocarbon because we can make a carbon-carbon bond without having to worry about getting rid of the oxygen, right? If we use a Grignard or a organic lithium, we would have to deal with removing the hydroxyl group to go to a hydrocarbon. And the bond that we made was this. Oops, almost did that wrong. Right there. But you can see with the synthesis, it really depends on what your starting material is because, heck, I could have made any carbon-carbon bond. Any carbon-carbon bond. There are some restrictions to the type of GILMAN you could use, and let me just double check this. For instance, if the you don't want anything too crowded, so you want to have that carbon either be primary or secondary. You don't want it to be tertiary. But honestly, that is the only restriction that I am worried about. Maybe there are some textbooks that say that this cannot be very crowded, but again, I don't mind if this is either primary or secondary. Now, what's great about this is that you could add an alkyl group to a carbon-carbon double bond, which is actually very odd. For instance, if I have this molecule here, yeah, let me draw this one right here. Give me 1 second, right there. Okay, it's actually very hard to substitute right here, correct? But now, not only can we substitute right here, we can substitute just a plain alkyl group, which is pretty remarkable. That's what's great about this GILMAN, that you could add to an sp2 carbon just plain carbons, nothing else. And let's give us a longer chain. Let's give us a butyl group. Copper lithium. Okay. Following your simple template. Can you draw me the product between this alkyl halide? It just happens to be, it's called a vinylic bromide, and this GILMAN reagent. Can you draw that there? The clue is put a dot on the carbon that you are attacking. Okay. Pause the video and draw me the product. Okay, what I would draw first is probably the alkyl halide part. Okay, and then that got replaced with 4 carbons. And the point of attachment is this carbon here, the last one, or the first one, depending on how you want to look at it. 1, 2, 3, 4. Again, I am warning my students, it's very easy when you're rushing or under the stress of an exam to draw the wrong number of carbons. You have a C4, C4, it's a C8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that is the GILMAN reagent. Shall we do a couple of problems? Let's say I'm looking at some of the problems in a textbook. Interesting. Okay. Make this will be pretty easy, I think. Make this molecule here. Synthesis. From this molecule here. When I do a synthesis on an exam, or not even an exam, if I have a molecule that I need to target in the lab, that I need to make for a collaborator, what is dictating the strategy, the synthesis, is actually what starting material do I have available in the stock room. Over here, they're telling you you only have this available. Now, where are the other carbons coming from? In an exam problem, if they don't tell you or they don't restrict you, you could use anything you want. Okay, you could use anything you want, including, well, you have to use the starter material that they gave you. But these other carbons, 1, 2, 3, 4, 5 carbons, whatever it takes, whatever reagent you want to use, as long as it has those carbons, you're fine. Another thing about synthesis is that try to identify the bond that you are making. You are making a carbon-carbon bond, and it's between these 2 carbons separated by the dotted line. You have that. We could convert this into a Grignard reagent, and I wouldn't blame you if that was your first instinct, because Grignards were so useful in the past 2 videos with all of those reactions. But I'm not making an alcohol. I want to try to avoid that. I'm just making a hydrocarbon. Okay. I use a GILMAN reagent for that. Maybe I could use this alkyl halide and just grab a GILMAN reagent from the lab or the stockroom. Do you know what the GILMAN reagent should look like? Let's use our templates. It just looks like that carbon piece that you added connected to a copper on that carbon of attachment. So the difficulty here, honestly, is to draw it. And how would I draw this? Okay. I would draw it like this. We have this alkyl iodide plus, let me flip this around. That methyl group is on carbon number 2. Okay, and here's the trick. You want to have this carbon within the parentheses. So you draw a line and you extend outside of the parentheses. Okay, and if you really need to number it, that's perfectly fine. 1, 2, 3, 4. 1, 2, 3, 4. So I'm confident that that's the alkyl group that I'm adding. Now you just have to put it in the form of a organocuprate or GILMAN reagent, copper, lithium. What you can do is put a dot on the carbon you are attacking, right? This is a partial positive carbon. And then give this to a classmate and say, well, don't show them the answer. Ask them, What do you think I get when I add these two? And hopefully they'll draw something similar to this. Oh, I'm going to attach to carbon number 1. And what else is attached to carbon number 1? 2, 3, 4, and there's a methyl group on carbon number 2. And that does look like the target. But there is a different way. Using the same Gilman strategy, why don't I convert this to the Gilman reagent? Let's see if that works. I'm going to try to squeeze it down here, actually, because I want this all on the same page. So that's one way. Another way is I'm going to start all the way to the left. Because when I look at this carbon-carbon bond, and forget about the starting material, doesn't matter which one was the Gilman part half and which one was the alkyl halide half. I'm going to double check right now to see if it's possible to have the reverse. Let's have the Gilman reagent be the one with the phenyl ring. And the way to do that is, again, organolithium first to make, and then copper iodide. Oh, how would I draw this? What's the trick? Draw your carbon skeleton, draw a line that extends outside the parentheses, and double check that within the parentheses, is that literally what you want to add? I want to add this part to an alkyl halide that looks like that. That looks like that. So if I have this, 1, 2, 3, 4, there's your alkyl halide. Before I draw the answer, again, it's a combination of what? An alkyl halide plus a Gilman. But here, I listed the Gilman first. It doesn't matter. Gilman plus an alkyl halide. Okay. Again, give this, oh, man, that would have been a point deduction. I was so concerned about putting the right number of carbons in the parentheses, I forgot that this was a Gilman, and the Gilman is a copper-lithium reactant. Now again, I'll put my dot on the carbon that I'm attacking. I have the attacker, make a attachment to the dot, and off of that dot I have these carbons. Same exact target. So for this molecule, I have now two different ways, but both ways are still using my iodobenzene. Now, if I didn't have to use that and they said, or the test asked, make this via any Gilman alkyl halide combination, man, I could make the bond between 1 and 2, make the bond between 2 and 3, make the bond between 3 and 4. Okay, any carbon-carbon bond, except obviously the carbon-carbon double bond, right? You're making a single bond. Okay, again, I just want to emphasize it's awesome that you could put stuff onto a benzene ring. Okay, typically this is very unreactive. You don't normally substitute at this sp2 carbon, but the Gilman reagent can, and now we could alkylate. We could alkylate benzene rings using this method. Very interesting synthesis. Well, as long as I have 10 minutes, I do want to do a little bit of review. I wasn't planning on doing this, but since I have some time, and for my class this will be probably the last video for Unit 4, let me do a little review about making those alcohols. And I think in the previous video, we were making alcohols that had 3 different R groups. And man, maybe this is exactly what I had. Not exactly. I think there was an isopropyl group somewhere. But if I ask you, how many ways can you make this using a Grignard or organolithium? The thing is, There are more than 3 ways, I think. We'll have to double check that. Using organometallic. And maybe not the cuprate or organocuprate because we have this hydroxyl group. So you will assume that I mean Grignard or organolithium. Okay, that's the problem. One strategy is you could use a Grignard plus a ketone. And this is what we did in the previous video. If I make this bond here, remember this strategy, bond A, or I can make bond B, or I can make bond C. Maybe I should use arrows instead of trying to cut the bonds. By making the carbon-carbon bond indicated by each of these 3 ways, what am I doing? I'm just going to stick with a Grignard plus ketone. And that was the last thing we did, or maybe not the last thing, but this is an exercise we did in the second video. But are you forgetting the first video? The first video we used an epoxide. Take a look at this. Recall. I'll do this in green. If we had this Grignard and I reacted with this epoxide, very simple. The simplest epoxide, oxirane, and I did protonation at the end. What did I get? Look at my dot. Okay, I'm going to attack there. I'm going to take my Grignard and attack the dot. Did I do that? I added to the dot 2 carbons. But do you remember where the OH goes? The OH is on the other carbon because this bond breaks. So the OH is not on the dot. The OH is right here. Look where my bond disconnect is. Or look where I made the bond. I didn't make the bond here. I made the bond 1 carbon away from the hydroxyl group. Can I use that strategy to get some other ways? I know how to do, I think this is the easier of the two, I know how to make this molecule via several different combinations of Grignard plus ketone. But what happened to the Grignard plus epoxide? Where are those dotted lines? Let's see if this is possible. It may not, I may have walked into a corner. Let's see if this is possible though. I'm redrawing the target. Oh, I think I might have messed up. I'm trying to figure out, see what's important here is that you attack the less substituted because you're using the Grignard in the presence of no acid. Oh, got it. Take a look at this bond right here. We'll call this bond D. Do you notice that to make this bond, I would have a Grignard reagent that looks like this, a 2-carbon Grignard reagent, attacking this carbon next door. So my dot is here. If you think about the type of epoxide that this piece came from, that epoxide is possible. Okay? Well, we might come back to A, B, and C, but I think people are freaking out about D. If we make bond D, this is what I would use. Okay, I'm making this bond right here. My epoxide is going to look like this. There's my dot on the right, and on my left, I have these 2 groups. Ah, do you see how if I attack this dot and open up the ring, I am going to get the OH on this carbon right here. What do I want to open up the dot with? I want to open up the dot with this Grignard reagent. Or you could use organolithium. And then I'm going to protonate the O- that I make. Okay. Again, if you want, you could draw like a pseudo mechanism, but really you're attacking right here. and then you're opening up this ring. You're attacking the less substituted carbon, and what we get is this. Hopefully it's the target. Okay, and then there's your dot and 2 more carbons. That target looks like good. Looks like our target. This is a check. This is for bond D, right here. Well, could we go from the other side? Bond E would bond E be this one here? Or would it be this one here? We've already know how to do this bond right here. That's bond A up here. To make this via an epoxide, I would have to make this bond here. Okay? So my challenge to you, and you could do a self-test, is if I'm making bond E, I'm not attacking a carbonyl group. I'm not attacking a ketone. I'm attacking this carbon here. Right? If I attacked a ketone, wouldn't there be an OH right here? What I'm doing is I'm attacking an epoxide. How would my epoxide look like, and how would my organometallic look like? Okay? We can switch it up. Let me draw the organometallic like this. CH3Li, organolithium. Also, I'll put the organometallic here, and I'll put the epoxide as reagent number 1. All you have to do, take your thumb, cover up what you added, just pretend that that oxygen is connected to the dot. Wouldn't that be an epoxide right there? And we have this dot, O, that. We just have now to copy what else is connected to this carbon right here. We have a 1, 2, 3 carbon chain, and I have again this is called an allyl group because it's connected from the allylic carbon. Don't forget that if you are doing a synthesis, you do have to protonate the oxygen. Okay, and this one's easy, or at least easier to draw the result, because basically I have everything with the oxygen containing part. Here's your dot, and let me just copy the rest of the right hand side. But what is connected to the dot? A methyl group. Methyl. Now double check. Does that match this? Yes. These two are identical. So that is bond E. Could you have made bond F? For bond F, very interesting, you would have to attack this carbon right here. And yes, let me just visualize this. So what am I visualizing? I'm visualizing that this is the Grignard or the organolithium, 2 carbon piece, and I'm attacking an epoxide that includes that dot. And that will work. So at home, you will do strategy F. Okay, let me zoom out. Oh, you don't see that. Strategy F. There's your F. And as practice, you will do strategy A, B, and C. Again, our goal is this molecule here. Okay, and if we zoom out, there are 2 ways to do that. You could do it via Grignard plus ketone, or organolithium plus ketone, and the other way is via, and I didn't actually write this, Grignard plus epoxide. I was a little worried that we wouldn't have all 3 combinations, but it looks like all 3 are possible. You will verify that by making bond F. When would it not be possible? It would not be possible if, when you do your analysis, if you're attacking a carbon that's more substituted than the other carbon. See, look at this. In each case, I had to double check that if we attack the less substituted carbon, that we do in fact get the product. Again, a lot of organic chemistry is trial and error. You don't want to just sit there just wondering, get it on paper, and if it doesn't work, you neglect that strategy or you try a different strategy or a different combination.